In today's pre-lecture screencast, the goal is to learn how to determine using a statistical test, the chi-square test, whether your observed data agree with an expectation, in this case one based on Mendel's law. The expectation is also considered to be a type of null hypothesis. It's important to take away not only how to do a chi-square test, but how to estimate the number of degrees of freedom and also how to interpret the p-value that's produced from the statistical test. First, let's look at Mendel's data. In these single-factor crosses, or monohybrid crosses, he saw a lot of F2s that had this typical approximately 3-to-1 phenotype ratio. But you'll notice that none of these ratios are exactly 3-to-1, and 3-to-1 is what's predicted or expected based on his first law. So let's focus on analyzing his data that are the farthest from being in a 3-to-1 ratio. So let's look at yellow versus green pods, which only had a ratio of 2.82 to 1. The basic question we're asking is that ratio, 428 green pea pods to 152 yellow, close enough to a 3-to-1 ratio to support Mendel's conclusions? The first thing we need to do is we have his observations. We have observed, which I'll just abbreviate as O, 428 green and 152 yellow pea pods. That gives us a total of 580 pea pods that he studied. Our first task is to determine how many of these two colors of pea pods would we have expected to see if Mendel was right and there's exactly a 3-to-1 ratio. The key here is that the number of expected individuals having these traits has to total the same number as were actually observed. So how do we calculate these numbers? Well, we just said that the expectation is that these values, whatever they are, be in a 3-to-1 ratio. So there are 4 total parts. So a fourth of 580 gives us that number, and 3/4 of 580 give us what he would have expected, what Mendel would have expected in terms of numbers of green pea pods, that is, if he had gotten exactly a 3-to-1 ratio that totaled 580 observed peas. So those numbers would be 145 yellow expected if there's exactly a 3-to-1, and 435 green. So that's pretty doggone close. The observed numbers and what we would have expected to see with an exact 3-to-1 ratio are really close. The problem with saying something like really close is that it's not quantitative. One scientist might say something's really close, another one might disagree. So what we need to do is to have some sort of quantitative metric, a measurement of exactly how close are these numbers, and that's where statistics comes in handy. So the way that scientists ask whether or not an observed set of data matches expected set of data are to perform a statistical test. And in this case, we are going to use the chi-square test. This is a statistical test that's used to ask whether an observed number of counts, that is, Mendel was sitting in his garden counting numbers of pea plants, or in this case, pea pods, of different colors. So when you have actual values of numbers of observations, never, ever frequencies or fractions. Numbers of observations, you use the chi-square test. So in this case, the chi-square formula says that we take the observed value, subtract the expected value, square that, and divide it by the expected value. Now the trick, or one trick anyway, about the chi-square test is you have to do this for every category. In the case of phenotypes, like Mendel's using, he's got two different categories. He's got yellow, and he's got green. So to conduct this chi-square test, we need to calculate the observed numbers of yellow plants minus the expected number of yellow plants squared over the expected number of yellow plants. And we need to add that to the observed number of green pods minus the expected number of green pods squared over the expected number of green pods. That will give us a value called the chi-squared test statistic. That's our first goal. So let's plug in our actual values. We have 428 observed minus 435 expected squared over 435. Square the difference first and then divide by 435. And add to that the difference between 152 and 145 squared divided by the expected value. And this gives us that chi-squared test statistic, which in this case is 0.45. At this point, we've done much of the hard work. Setting up the chi-square formula really is the most difficult part of this process. But now we have to figure out, what do we do with this chi-squared value? How do we interpret it, and what does it mean? We have to talk about one more thing first, before we can get into what does the chi-squared test statistic mean. And that's to discuss the concept of degrees of freedom. This is an important statistical concept. I'm not going to go through the gory details at the moment. Suffice it to say that the number of degrees of freedom in the case of chi-square tests is equal to the number of categories minus 1. So remember, in this case, when we're looking at phenotypes of a monohybrid cross, there are usually just two. There's a dominant and there's a recessive. So in this case, remember, we had two categories. One was the yellow peas, one category was the green peas. So the degrees of freedom for the current test that we're looking at is 2 categories minus 1, which means our number of degrees of freedom for this case is 1. So with a chi-squared value of 0.45 and degrees of freedom equals 1, now we're ready to figure out whether or not Mendel's observed data are similar or different from his expectation of a 3-to-1 ratio. So you'll notice this red box in the left column, labeled DF, is where you select the numbers of degrees of freedom. We have 1, so we're going to be looking at values in the first row, and this is where we look up the chi-squared test statistic value. So our goal now is to find out, where is 0.45 in this series of numbers. 0.450 is slightly less than 0.455, so our value is somewhere in this range between 0.016 and 0.455. It's pretty close to 0.455, but it's in this interval. Now what we do is we want to determine the p-value associated with this chi-squared test. And it's this top blue part that tells us the p-value. And in our case, what we want to do is find out what part of the header here corresponds to the place where our chi-squared test statistic falls. So if the chi-squared test statistic is here in this vertical red line, that means that our p-value is anywhere between 0.9 and 0.5 in this interval. Pretty close to 0.5, because the chi-square value of 0.45 is pretty close to 0.455. As another example, let's say you've got a test where you've got 9 degrees of freedom and a chi-square test statistic value of 21. You'd find the row with 9 degrees of freedom, move until you hit that test statistic value of 21, which is about here, and then you read up into the header to find out the associated p-value. And the p-value is the goal. We're trying to figure out what p-value is associated with our chi-squared test statistic. So we got a p-value of approximately equal to 0.5. What does that tell us? Well, scientists have generally agreed that a p-value less than 0.05 is necessary to achieve what we call statistical significance. What does that mean? In short, when p is less than 0.05, we conclude that the observed values are not equal to the expected values. The interpretation is that our observations, and this is what you would write if you were a scientist and were writing the conclusion of a statistical test, you would write that the observation is statistically significantly different from the expected values. Yet another common way to say this is that the null hypothesis is rejected. Again, just another way of saying that the expected values of the null hypothesis do not match what we've actually observed, the data that we've collected. Put one more way, a p-value of less than 0.05 corresponds with less than a 5% chance that our data truly do match the expectation, but look as different as they do just because of bad luck or by chance. Put one more way, when you have a statistical test where the p-value is less than 0.05, that means there's a greater than 95% chance that the result is true, that the observed values do not match the expected values. So in this case, what does it mean that with Mendel's data, we observed a p-value of 0.5? 0.5 is much, much larger than 0.05. So this lies in the category of observed matching expectation. That is, there's no statistically significant difference between Mendel's observations and his hypothesis that you would see a 3-to-1 ratio. And in all of Mendel's single-factor or monohybrid crosses, his data all matched the expectation of a 3-to-1 ratio. There were no statistically significant differences between his observed or expected values. To recap, to do a chi-squared statistical test, first we obtain observed values. Then we calculate expected values, which is part of the null hypothesis. Calculate the expectations. 3, we plug those values into the chi-squared formula, and we obtain the chi-squared test statistic, single numerical value. 4th, identify or determine the numbers of degrees of freedom, look up the corresponding p-value using your degrees of freedom and the chi-squared value, and then lastly, interpret the p-value.